All
All
right.
right. Welcome back to the grad student seminar, everyone. I'm pleased to introduce our speaker for today, Yoon-Joo Kim, who will be talking about schemes.
Right. Thank you for inviting me. Yeah, so I'm gonna talk about what a scheme is today. So if you don't know what a scheme, it will be I don't know, a good opportunity to learn what it is. I'll try. So before starting the talk, the disclaimer is, of course, I'm not going to like explain what a scheme is exactly like literally what a scheme is, but I'll try to sort of give you the idea. So all the definitions like written up here are not the most general definition that people use. So if you, for example, like go into the Wikipedia and then just type what a scheme is, then you will see a different definition. And that's because I've simplified the definition a lot in the situation we're dealing with, not the most general situation as you can think of. Anyway, so let's start. So let me start with the algebraic varieties. So the algebraic varieties are very intuitive, and maybe it's just a natural object to think of. But what is an algebraic variety? An algebraic variety, so here, I told you the algebraic variety here, what I mean is not the most general definition of the algebraic variety that people have. So we're gonna mostly concentrate on the affine algebraic variety over the complex number. But anyway, we're gonna just drop all those adjectives and I'm just gonna call it algebraic variety. An algebraic variety is simply the zero set of just a finite collection of polynomial systems. So you have finite collection of polynomials, f1 to fr, with n variables, with x1 to xn variables, and then you can just consider the zero set of those polynomials, and I'm going to define that set as an algebraic variety defined by this system of polynomial. That's it. So this is a very natural object to think of, because like who doesn't want to solve a polynomial equation, right? So let me give you a bunch of examples first. So first, if you stick to the let's mostly stick to the C2 as an ambient state, meaning that we have two variables, x and y, x1 and x2. So C2 inside of C2, the whole set is an algebraic variety, because the C2 can be realized as a zero set of an empty set of polynomials. You don't have any defining polynomials, and C2 is the whole zero set, right? So you can think of it like that. It's a bit of a anyway. So C2 is an algebraic variety according to this definition. And of course, if you want to solve the equation, the single equation x equals a inside of the xy plane, C2 plane. So of course, I can't really draw the C2 in this two-dimensional space, in this two-dimensional my iPad, meaning I should really restrict to the R2 situation, but I think it's like pretty much instructive. So I'm just gonna draw C2 in the following planar way. Anyway, this x equals a solution is certainly this line, as you all know. So this is an algebraic variety inside of the C2, defined by one single equation. And what's the third example? My third example is I want to solve the system of polynomials x equals y equals 0. And obviously that's stupid. This is 0. The origin is my algebraic subvariety of C2. This is C2. All right. And number 4, I can think about a little more complicated example. I want to solve this equation, y squared equals x squared times x plus 1. And then it turns out the solution set of this equation is like a pretty curve, something like this. This is actually called a rational nodal rational curve in terms of algebraic geometry, but you don't need to learn that. You don't need to know that. Anyway, this is an algebraic subvariety in C2 in terms of our definition. So a non-example is, of course, a graph of y equals e to the x. You're not allowed to use the e to the x because we're only concentrating on the polynomials. You don't everything we are talking about today is about just polynomials. You don't want to think about exponential sign and like every like crazy bump function. We don't want to think about. This is a non-example. Okay. All right. So yeah, so far so good. So remember, our definition of the algebraic variety is literally just a zero set of polynomial equations. So if you solve the polynomial equation and then you just plot all this point, that's the definition of algebraic variety, meaning that our definition of an algebraic variety is just a set, right? It's a set of some complex space, C to the n. But if you want to do a geometry on that set, then well, the definition of geometry varies people by people. But here I mean by geometric space, what I mean is you endow with topology on a set. Yeah, so that seems reasonable. And the second condition I want to endow, axiom I want to endow is decide what functions would you allow on that set. So what I mean by that. So let me give you a simple example about the manifolds that we know all know about. So manifold M can be think of in this philosophy. It can be think of a set equipped with a Euclidean topology. So far, so good. And then next, you need to decide what function you should allow on that manifold. So if you only allow the continuous function on M, then that'll give you the notion of a topological manifold structure on your manifold M. So if you allow the C-infinity functions, then you will have a differential manifold structure on your manifold M. And if you allow analytic functions, then you have a notion of an analytic manifold. So in terms of that, the decision of what function we should allow sort of decide what property that space, geometric space, has. Well, so in terms of that, the function discussion for algebraic varieties, we already have the answer because I just told you, right? The only functions we should think about are just polynomials, right? So we already have the answer. So for example, if you consider the algebraic variety C2, then of course we want to allow only the polynomial functions of the two variables C, X, Y, okay? So if you consider this algebraic variety X equals A, then because this is a line, this is C, this is a line, so we only want to allow the polynomial function Cy over this algebraic variety, right? Because it only has the Y coordinate, the X coordinate is fixed. If you consider this algebraic variety a point, then of course only the constant function should be allowed, right? But if you think about the fourth example, this polynomial, this algebraic variety is a little complicated. So we don't really have the answer. Yeah, maybe it's like not that trivial. Okay. So I'll give you
a dumb question.
Sure.
Which is, can you say more about what you mean about allowing functions on the set?
Oh, so this is more like a philosophy, I would say. So like I think the best example is a manifold. So the definition of the manifold that we all agree of is, it's a locally Euclidean space open ball hashed together with a transition function given by the C-infinity function, the analytic function, so whatsoever, something like that, right? So you can actually, a little bit of more algebraic geometry viewpoint is that you can, the equivalent definition of that is the transition function part is to endow what kind of functions you can allow on your manifold. So you decide the topology on your manifold first, and then to define what a transition function is, that's equivalent to saying what functions you are allowing on the manifold. It turns out, this is a non-trivial equivalence, but it turns out that's a little more algebraic perspective of your manifold. And I'm sort of taking this aspect to define the notion of an algebraic variety.
Okay, so basically the transition functions, is what we're talking about, or
right.
Something
this is essentially a transition function, exactly. So if you want to patch the algebraic varieties to get something like that, then you need to decide what transition functions you should allow. And I'm just allowing the polynomial function as transition function. That's all I'm talking.
Okay.
Yeah, thanks. Okay, right. Right. So returning to our original discussion. Okay, so these are actually all motivations. I don't know if it motivated you, but so if you have an algebraic variety defined as a zero set of a bunch of polynomials, and then I'm going to define a new concept called a coordinate ring. So what's a coordinate ring? My coordinate ring is a ring, commutator ring, defined by the quotient, the ring quotient of this polynomial ring, by the ideal defined by these set of polynomial, my defining equations. Okay. So this is an ideal generated by these, and so this is a quotient ring. So you can consider a quotient ring of this polynomial ring, and then you can consider this coordinate ring as exactly the function that you should allow on your set algebraic variety zero set on the algebraic variety X. Okay. Right. So I can't really justify this very much, but let me give you a bunch of examples. On those examples, for example, if you consider an algebraic variety X equals A inside of C2, and then I just told you what we want to allow, the polynomial function on this algebraic variety seems to be Cy because we only have the Y coordinate. That's only the free variable, right? So how do we recover that? Yes, we do, because you have your algebraic variety defined by the equation x minus a equals 0, meaning that according to this definition, your coordinate ring should be the quotient of your polynomial ring by this defining equation. And that's exactly, if you recall the rings theory that you have learned in the comps course, this is actually isomorph to C of y because you have identified x equals a, meaning that our coordinate ring is exactly the desired function that we should allow. And similarly, if you consider the point inside of C2, your defining equation is x equals 0 and y equals 0, meaning that your coordinate function, coordinate ring should be this quotient ring. And then because you have cxy, two variables, and you mod out two variables, and then you just get a constant function. That's exactly what we wanted. So I'm just justifying, that coordinate ring is exactly what we want. And similarly, I can now give you the answer what function you should allow on this difficult algebraic subvariety is just simply a quotient ring of cxy by the ideal defined by the defining equation. So that's exactly the function what we should allow on this algebraic variety. All right, so now I can enhance my definition of an algebraic variety, not just as a set, but as a geometric space in the following way. So an algebraic variety is by definition a zero set of polynomials in the previous sense, equipped with my topology, which is called a Zariski topology. I'm not going to talk about Zariski topology too much in this lecture because it can be a little technical. So Zariski topology, ignore it, but we do have a well-defined topology on it. And thirdly, I need to equip a function, right? I need to allow what function we should what function we should allow. And then that is exactly my coordinate ring. So that three triple together is my definition of an algebraic variety. And this is a very natural object to think about. People have thought about it like more than 100 years. And like all the algebraic geometry is built in under this algebraic variety. We can do a lot of geometry on it actually, right? Yeah, so questions so far on the definition of an algebraic variety? No? Okay, good. So, right, so algebraic variety is like very, very good. So we study that a lot, but it has a little bit of problem. To see what that problem is, so we need to first understand what a Hilbert null sentence set is. So this is a very old theorem of Hilbert, which is a very fundamental theorem in the algebraic geometry. And this is actually a generalization of a fundamental theorem of algebra. Let me explain that later. So anyway, Hilbert in 1893, about like 130 years ago, proved that given an algebraic variety X, there exists a bijection between two sets, the points in X and the maximal ideals in your coordinate ring. Okay, so this seems like a very random theorem, but actually this turns out to be a very important theorem. So let me give you an example first before I talk about the corollary. So if you think about an algebraic variety C, then the coordinate ring is definitely C of X because, over a line, you have only one variable, and meaning that you have the full polynomial as a function. Anyway, so if you apply the Hilbert null sentence as this theorem into this situation, then you should get a one-to-one correspondence between your algebraic variety, the given algebraic variety, and the set of maximal ideals inside of a coordinate ring. So what is this one-to-one correspondence? It turns out, by the fundamental theorem of algebra, every maximal ideal in Cx is a principal ideal generated by a degree 1 polynomial x minus a, where a is a constant, a is just this complex number, right? Because if you have a degree 2 polynomial, for example, then any degree 2 polynomial fx can be factorized by x minus alpha, x minus beta, meaning that this is not a maximal ideal. So all the maximal ideal means that you consider the irreducible polynomials, and the irreducible polynomials in Cx is just degree 1 polynomial by the fundamental theorem of algebra. So this is the reason why you have only x minus a. And of course, that corresponds to this a inside of C. And this is your one-to-one correspondence. This is Hilbert null sentence sets. So it turns out this is a very, very powerful theorem, even generalizing the fundamental theorem of algebra. But so what's the moral of this in terms of our algebraic geometry discussion? So what this means is that actually, if you start with an algebraic variety X, and you can define a Zariski topology, whatever that is, and you have this coordinate ring, right? I told you this is my definition of an algebraic variety. But it turns out if you know the coordinate ring, then you can determine what an X is, because you just consider the maximal ideals, and that's what your set X is. So the coordinate ring is the most important part in the algebraic variety definition. And if you know the coordinate ring, then you know what this X is. And you also, it turns out you can also determine your Zariski topology. So the thing is, actually, you don't need to think about the triple. You only need to think about this AX, and that determines your triple. So the ring determines your algebraic variety. That's the point. That's what people realize after Hilbert's Nelson and Satz. So let me give you, right, so that's that. And then after that, like a technical problem arises. So this is the first problem that we encounter. For example, let's consider the equation x squared equals 0, okay, the stupid equation. And then if you solve it, then of course you have this with this y-axis. That's the solution set of this x squared equals 0. And of course, that's equivalent to x equals 0, because solving the x squared equals 0 is the same as x equals 0. That's of course true. So the point is, so should the coordinate ring of this algebraic variety, this guy, the quotient of cxy divided by x squared, which is the defining of x squared, or is the defining equation just x? Because those are the same. If you solve the equation x equals 0 and x squared equals 0, those give you the same algebraic variety. But it seems like the coordinate ring has a little bit of subtlety. You can't really decide what coordinate ring you should use. So the classical algebraic geometry gives the answer that actually the coordinate ring should be this one. And why is that? Because in the classical algebraic geometry, people emphasize more about the algebraic variety itself, the set itself. The algebraic variety in the simplest form should be defined in the x equals 0, not x squared equals 0, so that you can justify your AX should be this quotient by just not x squared, but x, and then because it's a line, it has to be isomorph to CX. Okay, that's the answer in the classical algebraic geometry. But after Grothendieck, everything has changed. And Grothendieck told us, actually, you know what? Forget about the algebraic variety, forget about the 0 set. Only the polynomials are important. So you should really define your polynomial, the functions, the coordinate ring as cxy divided by x squared. And then what is your algebraic variety? Then like it turns out, there's a very subtle question, because even if your algebraic variety x equals 0 and x squared equals 0, they are the same, right? They are the same line. Grothendieck is saying that one algebraic variety should have coordinate ring this guy, and the other algebraic variety has coordinate ring that guy. So there's a you don't know which one you should choose. So the problem here is that the algebraic variety definition has a little bit of problem. That's a point of Grothendieck. So let me give you the definition of a scheme defined by Grothendieck in 1960. Of course, Grothendieck didn't define it by himself. Like there were a lot of like collaborative Grothendieck, including Serre, and like all the like big mathematicians, Zariski, they have all contributed to this definition. But like, Grothendieck really wrote it down first. So if you have an arbitrary commutative ring, so you can think of this as a coordinate ring of an algebraic variety, AX. Then you define what's called a spectrum of A. That's the standard notation. Spec of A by a triple, a set, a topology, and the function. Okay. So my set is a set of maximal ideas in A. And that is the that can be justified by the Hilbert-Nelson and Satz, right? Remember the Hilbert-Nelson and Satz? So Hilbert-Nelson and Satz says that if you have an algebraic variety, then your algebraic variety X can be recovered from the set of maximal ideas on your coordinate ring. That's exactly why we have chosen the set of maximal ideals as a set, as an underlying set of our scheme. And the Zariski topology, we're going to ignore this in this talk. And lastly, that the function is just A, the stupid A. So if you define this triple as a spec of A, then I'm going to call the spec of A an affine scheme, or just a scheme in this talk. Okay. Everything good? Any question?
I thought you take prime ideas, not maximals.
Oh, right. So yeah, so I want to point you out that this is not a this is a simplified definition. Right. So that's actually a good point. So right, maybe I should have mentioned this. So this definition, spec of A, is a little bit of simplified definition. So the arithmetic's original definition considers not only the maximal ideals, but also prime ideals in the given ring A. And to motivate that, I need to talk about a little bit more on the what's called a generic point, but I didn't want to do that in this talk because it will, it's already very complicated. I don't want to confuse you more. So I'm just concentrating on maximal ideals. And also this has to be a little changed if you want to adapt like a very general definition. This has to be changed into what's called a structure sheet, if you have heard about that before. But also I don't want to confuse you more talking about sheaves. So in this situation of spec A, turns out the structure sheet is equivalent to just considering the ring itself. So I'm just putting the ring as a allowed function. Anyway, so this is not the most general definition that you have in the Wikipedia or Hartshorn. So let me give you an example. So we have just talked about like a couple of minutes ago. C2 has the coordinate ring CXY because it has two free variables, meaning that you allow all the polynomials of two variables. This is your coordinate ring. So if you know the coordinate ring, then you should be able to recover your C2 in terms of the Hilbert null and sets, and you're recovering in terms of the spec. So the spec A was by definition the set of maximal ideals in CXY. So you should recover C2 in terms of growth and null sets, and then you equip as a risky topology, and finally the ring itself into the spectrum of the CXI, and that's exactly the same as C2. So forget about C2. This is more important because you can recover the C2. So if you consider the spec of CXY mod out by x equals a, and then you can interpret this as a defining equation of set of defining the zero set of x equals a inside of C2, which is our original previous example in C2. So this line corresponds to spec of CXY mod out by x equals x minus a. And this is the coordinate ring. Okay. And the way algebraic geometers argue that this is actually isomorphic to the original line C is that your coordinate ring, this guy, is actually isomorphic to CY, which is the coordinate ring of the honest line. And this proves that this is actually isomorphic to the honest line, C. This is the algebraic geometers proof. A little bit more complicated than the usual one. Well, yeah, so let me return to that pathological example. If you consider the coordinate ring, if you consider the ring CXY divided by x squared, then this is not the line. This is not the same as a ring. This is not isomorphic, CXY divided by x. This is not isomorphic, meaning that spec of that guy is not the spec of that guy. So what is spec of this guy if it is not a line? It turns out that it actually has a geometric meaning. So the geometric meaning is that you consider the zero set of x squared, which is just this line. But because of the x squared term, you also consider the infinitesimal data, like a derivative data, if you want to say. So we actually have a precise language of how to record the derivative of a function in terms of this ring, inside of this space. There's a very, this is a very rigorous way to capture the infinitesimal information of this. So classically, what algebraic geometry did in this kind of situation, they call this as a double line, because it seems like you have the two lines, right? This is x squared has multiplicity 2 issue. So this time, this is double line, this line times 2. But now we call it as a spec of this guy, spec of this ring, which encodes that double line information, the infinitesimal ring data, infinitesimal. Okay. So that was a definition of a scheme. Question about that? No? So yeah, so I think I'm going a little faster than I expected. So I want to justify by showing you a bunch of examples, justifications why the schemes are more important or why schemes are more interesting than the varieties. So why do you even consider schemes? Okay. So the obvious question is, if you see the definition of scheme for the first time, why do you even care about such a complicated object? Why do you even, why don't you just stick to the varieties? Because that's easier. Right? So to understand this question, to answer this question, you need to understand the history, a little bit of history of algebraic varieties. And of course, because the algebraic varieties are the most natural that you can think of as a zero set, literally the zero set, people have thought about algebraic varieties a lot. Like in 1900s, like early 1900s, late 1800s or something like that, people have studied algebraic varieties a lot. And it turns out there are tons of theory, beautiful theory about algebraic varieties, okay? And then people wanted to generalize that situation a little more outside. Maybe we can, increase the dimension. Maybe we can consider a little bit of a more general situation. And then suddenly what happened was they came out all the various technical problems which cannot be captured by the language of algebraic varieties. And then like the theory became a mess. So for example, people had to introduce the notion of what's called a generic point. And this is a very intuitive, but like a very non-rigorous concept at that time. And they also needed to, introduce the variety with multiplicity, as we just discussed, this variety, the line times 2 with multiplicity, they needed to consider that, but they didn't have any language to realize that. And they also needed to deal with the singularities. What if the manifold or the algebraic variety is non-smooth? And then to do that, you actually need the language of schemes. The algebraic variety is not enough to deal with the singularity situation, and so on. There are various technical problems arise, and people sort of like dealt with those kind of technical problems ad hoc, in a very ad hoc manner, and it's often non-rigorous and it's very ugly. Okay, so the problem was like actually like the accumulating. So people realized that issue. It was a serious issue. So in 1940 to 1950, a great mathematician, his name is André Weil. He himself was a great mathematician. He's a great algebraic geometer and great number theory. He's a genius. He tried to sort of rewrite the whole foundations of algebraic geometry in his own language and his own setting. It was a very huge project. Nowadays, this is called a Weil foundation. And sadly, Weil foundation is abandoned nowadays. Anyway, so he tried to develop his own theory, the foundation of algebraic geometry, so that you can make all these discussions very rigorous, not a non-rigorous like an ad hoc way. But so he was sort of able to make this discussion rigorous. But the downside of this foundation is that it was very complicated. It was like super unnecessarily complicated. You have to deal with all those like technical. Yeah, I don't know. Definitely don't know the Weil foundation much. No one studied the Weil foundation nowadays. But what I know is like it's very hard to learn. Okay, that was the situation in the mid 1950, and suddenly, a person whose name is Alexander Grothendieck just popped out, and then he invented the notion of a scheme, and then he got a Fields medal from it. He got a Fields medal from define the notion of a scheme. So Alexander Grothendieck in 1960 with his collaborators, they're all great mathematicians, invent the notion of a scheme. And this scheme, notion of a scheme, resolved all these technical issues, like everything, every single thing was like completely explained by this notion of a scheme. People were very excited about it. So like quickly, the foundation was, they abandoned the Weil foundation, they adapted the notion of an algebraic scheme. And, we've been adapting that for 60 years now. So that's a reason why people were thinking about schemes. Okay, so let me sort of give you the moral reason why the scheme theory is powerful, and it solves all the technical problems that arise in the variety theory. So recall that our definition of a scheme is given any commutative ring A, you define a scheme spec of A by the set of maximal ideals equipped with what's called a Zariski topology and the ring A itself to endow the notion of a function on the spec of A. Okay, so these three triple makes the spec of A a geometric object, not only a set, not only a vector space, the topological space, but actually a geometric object by this endowing this. So if you know the notion of a scheme, then you can deal with the algebraic geometry over the real numbers, which was totally impossible in the classical setting of algebraic varieties. And why is that? So think about, let's try to solve the equation x squared plus y squared inside of R2. You only consider the real situation. Then this is literally, if you draw the picture, this is literally R2, the plane, and the x squared plus y squared plus 1 is, as you know, there's a circle. And this is an algebraic variety. The algebraic zero set of the x squared plus y squared equals 1. It's a very well-behaved circle. And then people wanted to do algebraic geometry over this circle because it's a zero set of a polynomial equation, but somehow it didn't work. Somehow the theory didn't work. And the reason is exactly because this was not a scheme. Your algebraic variety Y is not a scheme, because if it were a scheme, then it should be realized as a spec of A, where A is a coordinate ring. The function you should allow on this algebraic variety, which is precisely the quotient ring of Rxy divided by this defined equation. So the question is Y a scheme defined by the spectrum of this defining the coordinate ring? The answer is no, unfortunately. Actually, the scheme spectrum of A contains more points than what you can see in this simple circle, because the notion of a scheme encodes what's called a C points, the complex points. So the point here is so the upshot here is that even though you can see only the circle inside of the picture, they're actually hidden points. They're hidden points you cannot see in this picture. And if you deal with the algebraic geometry over the real numbers, then you somehow need to consider all those hidden points together. And that's exactly why the algebraic variety is not enough. If you consider the scheme, then you can see those hidden points, which you cannot see in the algebraic variety picture. So yeah, that was exactly the reason why classical algebraic geometry, they had no idea about the algebraic geometry over R, but now we can with the language of schemes. There's a systematic study of the real algebraic geometry. Actually, you know, like I think Oleg Vieira is an expert in the real algebraic geometry in this department, right? Our department. Right. So that's one, you know, hint why the scheme theory is more important than the algebraic variety theory. So I can give you an even worse example. So let's consider the equation x squared plus y squared equals -1 inside of R2. Okay. And then the coordinate ring is, of course, defined by the quotient of your polynomial ring, mod out by the defining equation, that ideal. That's your coordinate ring, which is well defined. But if you actually solve this x squared plus y squared equals -1 inside of R2, then of course there's no solution. The algebraic variety is just an empty set. So there's no theory of algebraic varieties with the polynomial solution of the polynomial equation, this guy. But actually, if you consider the spec of this ring, then this is not empty. There are a lot of maximal ideals inside of this ring. Actually, if you remember like a comps problem or those kind of thing, any commutative ring contains at least one maximal ideal. So whatever the ring you choose, the scheme cannot be empty. So this contains much more information than this algebraic variety and empty set, and that allows us to define the theory of solving equation x squared plus y squared equals -1 over R. Okay. So this is conceptually very important. Again, a conceptually very important theorem developed by Grothendieck, but I think it's getting us too far. It becomes already pretty complicated, so I'm going to ignore this. It just morally says that considering a scheme is actually equivalent to considering a variety, but in a strict sense, this is strictly containing more information in the sense that you're not only considering the zero set of your original polynomial, but actually you're considering the zero set of all the polynomials with the field extension, with the ring extension. For example, like if you want to consider the equation x squared plus y squared equals in R2, there's no solution set. But if you consider the field extension CR, and then if you want to solve the x squared plus y squared equals -1 inside of C, then you suddenly have a lot of solutions. And it turns out the notion of a scheme actually is equivalent to considering all those zeros set together. So the notion of a scheme is very, very powerful. You're somehow solving not only your original polynomial equation, but also all the field extension, and then you solve the polynomial equation over that field extension. That's proved by Grothendieck. And yeah, let me just stop mentioning this. It's a little more complicated. So yet another example. Number theorists care about schemes. Why do they care about scheme? Because, for example, let's say you want to solve this equation, this innocent equation, over the rational numbers. So what rational number x, y, z satisfies x to the n plus y to the n equals z to the n? So of course, this is a very hard question. You guys all notice that. But at least theoretically, we have a foundation. We have a theoretical background to, you know, study this equation, which is just a spec of this coordinate ring. So solving this equation is actually equivalent to understanding what a scheme is. And the theory, this problem becomes very, very hard, because usually spec of these, like this Q coefficient polynomial ring is like insane. They're very hard to understand. If you have the C, then like this becomes an usual algebraic geometry, complex algebraic geometry. But if you change the coefficient to Q, then it becomes a rational algebraic geometry. It's insane. They're very hard questions, like just lurking around, even for the spec of Z and spec of QX, very simple examples. So anyway, the point is, the scheme theory at least provides a theoretical, you know, language to deal with this number theorist's interesting question in terms of algebraic geometry. Well, there's yet another example. So you can think of the schemes over the finite fields. So you might already heard that people talking about, you know, like what if you thinking about characteristic P algebraic varieties or something like that. That characteristic P algebraic variety is exactly a scheme over the finite field. That's what they're referring to. So for example, this, if you consider the field with P elements, finite field Fp, and then think about this ring, Fp generated by two variables, polynomial, and then mod out this x squared plus y squared, and then take a spec, that's equivalent to solving the equation x squared plus y squared equals 0 modulo P. So this also gives you a theoretical language, how to deal with the modulo P solutions. And that's called the finite field algebraic geometry, characteristic P. And finally, there's yet another interesting application of the scheme. So scheme also generalizes the Galois theory. So remember the Galois theory, the terrible theory that you learn in the what's it called, the comps exams? Oh my God, I don't want to remember that. So the Galois theory actually is a very simple example of a scheme theory in the following sense. So suppose you have a field K, and then K, a field is definitely a ring, right? So you can consider the spec of it. If you consider the spec of a field K, and it turns out there's only one maximal ideal of any field. Okay, so as a set, it's just a single point because there's only one maximal ideal. And your Zariski topology over this set is the singleton set, of course, becomes a discrete topology. This is like very, you know, it's very dull. But the power of the scheme theory comes because you also have the notion of a function. You're allowing K, your original K, as part of the data. You're encoding K as part of the data of your spec of K, meaning that if you have two different fields, K and L, if you consider the spec of K and spec of L, so the spec of K and spec of L both have a point as a set, and discrete topology as a topology on that singleton set, meaning that you cannot distinguish the spec K and spec L as a topological space. But because you already you also encoded your K and L as a part of the data of your spec of K and spec of L, they cannot be the same. So even though they're both two just singleton points, they are different. And this allows to think about a morphism between the two singleton sets, like a stupid morphism from a point to point. Of course, in the topological sense, this is nothing. This is a stupid theory. But if you consider scheme theory, then this is actually the Galois theory. And the Galois theory can be modeled as a morphism, as a covering map between a point and a point. Right, and then you can involve various topological theory of covering spaces. That's exactly why you call the covering space the Galois covering in the algebraic topology, because that's exactly the same as Galois theory via the scheme theory. And right, so this is yet another application of the scheme theory. And so how many applications do we have? Like at least 5, I think. I don't know, something like that. And there are like tons of more applications of scheme theory that you cannot even think of in the variety theory. And now with this technology, we can do a lot more algebraic geometry. So hopefully this convinced you why we should think about the scheme theory in algebraic geometry. Yeah, thank you.
Thanks, Yoon-Joo. Are there any questions?
So I have a question. I'm just sort of thinking about how to formulate it. But I mean, one thing that I found interesting earlier was when you were talking about algebraic geometry over the R. And so we were saying we have these, the variety is empty, but the scheme isn't.
Right.
So in some sense, and I'm really just sort of, summarizing my main takeaway of the talk. It's not really a question, I suppose, but I guess, and maybe I'm confirming my understanding, which is that, okay, so these schemes are geometric objects by how you've described. And so in some sense, real algebraic geometry is not so much working with varieties, but it's sort of studying geometry of schemes. Okay.
Right. So
it was very cool. So it was a great talk.
Right. Yeah. Thanks. Yeah. So with the language of algebraic varieties, you cannot deal with the algebraic geometry over the real numbers. Like you just can't. There's no systematic study. It's impossible. And the scheme theory is necessary if you want to deal with the algebraic varieties over the real numbers. And actually, that's part of the reason why most of the algebraic geometers only concentrate on the complex numbers, right? Most of the algebraic geometers in this department think about the complex number algebraic geometry, and this is like one part of the reason, because if you want to think about the algebraic geometry over other fields, then it's much more complicated. You have to deal with all the other technical difficulties in this sense. But if you think of algebraic varieties over C, then sometimes algebraic variety is just enough. You don't even need to think about the scheme because it turns out those theories are equivalent in the nicest situation. Even though you have a more general theory of schemes, some of the situation those theories are equivalent, so considering the algebraic variety just enough. And that's part of the reason why people stick to the complex number algebraic geometry.
Yoon-Joo?
Yeah.
I have a question. Does the Nussel and Suts, does that only apply for fields that are algebraically close?
So sorry, say that again.
The Nussel and Suts?
Oh, no, yeah, you're right. So you're absolutely right. So here,
and that's why it doesn't work for R, for example, or even
exactly. Right. So this is only for algebraic variety over C. Right. So if you consider, the real the situation we mentioned like 1 minute ago, that the real algebraic geometry situation is a counterexample for this theorem for the real, because this was empty.
I have a question about, oh, sorry, go ahead, Tim.
You first, Nathan.
I have a question about the Galois
Sure.
covering. So
don't ask me too much.
Yeah. I mean, I don't really know what's going on. So you have two fields here, K and L, and spec of a field is just topologically it's just a point.
Right.
But if you have a Galois covering, so you have some Galois group, does that give you like an action or maybe an automorphism?
Exactly. Yeah, you're right. So it turns out if you have a field extension, L contained as a subfield of K, then because L subfield of K, so this, if you apply the spec, it turns out you need to reverse the arrow, so you get a morphism from spec of K to spec of L, which is over here. Okay, and then this morphism is somehow not an identity map, and then this spec L can be considered as a spec K mod out by the group action, where the group action is precisely the Galois group. So somehow this Galois group is acting on this single point scheme K. I don't know how. And then if you mod out that action, then you get the smaller spectrum, also a single point. It sounds really stupid. And this resembles a topological, the covering map. It's a Galois covering. So the Galois covering is a topological covering. Galois extension is. This is impossible. Yeah, this is very funny, right?
Yeah, that shouldn't be. Yeah, okay. Anyways, thank you.
In the near the beginning of the talk, you were talking about, so we have these singularities, other points, and these pose problems, like technical problems, and this sort of motivates the discussion of schemes.
Right.
But I'm wondering if you can say a little bit. So I guess, can you describe this example of the double line, and I guess this is one such problem that you're talking about. But singularities, other things. I mean, what is it the same idea as the line, or is it different ideas for why these are problems?
So yeah, so to be honest, the singularity part, I haven't thought about it that much. I just put it here. So maybe the variety theory can deal with the singularity theory. Maybe it can, but like definitely if you adopt, okay, I can't think of it as the top of my head, but definitely the scheme theory should help to develop the singularity. Sorry, yeah. Right, but like the singularity, like, so I know historically singularities are not dealt with algebraic geometers before the invention of a scheme. So only after growth in the singularity, I mean, even after growth in the invention of a scheme, like only after like 20 or 30 years later, people have thought about the singularity theory like very seriously. So I guess like with the algebraic variety language, it's like even harder.
What I don't know what this means, like the singularity theory or something.
Right. So okay, let me actually, yeah, you got me. What do I mean by that? Yeah, so here the singularity is, if you want to see it in the picture, like, so here, this is the singularity of your algebraic variety.
Mm-hmm.
This is locally, if you choose a point here, then this is locally, smooth. But if you choose a point in the origin, then of course this is locally like a cross section, so which is not smooth. So you call this a singularity, and you study the singularity by the, actually, yeah. So, well, we can think about the singularity by the scheme theory in terms of the, so, right, okay. So let me give you this like 1 minute example. So in this situation, your defining equation is y squared equals this guy, and this is your, yeah. So at the origin, you have a singularity, and how do you detect that? How do you detect it as a singularity? So what you do is you consider the spec. Okay. So you consider what's called a completion of this ring. So there's a notion of a completion in algebraic geometry of a ring. And then what you get is you have like a formal power series instead of a polynomial ring. So you allow the formal power series like an exponential function formally. And then you mod out y squared minus x squared, x plus 1. And then in this formal power series, this x plus 1 is invertible because, I mean, like 1 over x plus 1 is 1 minus x plus x squared plus you have a power series expansion. So this is invertible. So this equation is essentially y squared equals x squared times a constant. And that's y equals plus minus x. And that's exactly why you have y equals plus minus x around the origin. And that detects a singularity. And well, okay, strictly speaking, you don't really need the notion of a scheme here because I've just used the ring theory. But it's obvious that this coordinate ring should be more emphasized to detect the singularity, and scheme theory like really just emphasizes the defining equation, which is the coordinate ring, not the variety itself. Yeah, I mean, okay, I don't know how to help you, but
So I guess, I mean, people just want to study singularities because they're interesting, and the schemes sort of help us do that in some sense.
technically,
is one of the ideas here.
So the scheme is a language. So what we have done so far, in the talk was we were just defining the manifold. Let's say we have just defined the manifold, and we have not developed any kind of theory of manifold so far. So this provides a language. So with this language, you can do all the other things. So this provides a foundation, like a language foundation, something like that. Mm-hmm. Framework, I would say. Yeah, sorry.
Okay, thank you.
Could you talk about what the complex points are?
Oh, the complex point. Right. So yeah, I didn't really explain what a complex point is. So here I gave you an example. Okay, so maybe this example will help. So recalling the situation. So our situation was solve the equation x squared plus y squared inside of R2. And then this is our algebraic variety 0 set. But I'm claiming that there are more points in the spectrum of A, which is a set of maximal ideals. So what is a maximal ideal that you cannot see in this real point? That's called a complex point. So let's think about formally x, y equals 2 comma, plus minus square root of minus 3, which should be the solution for this x squared plus y squared equals 1 over the complex number, right? Yeah, obviously you can check it. And then this actually is modeled as a maximal ideal because this is the 0 set of x minus 2 and y minus, this 3i. But this ideal is not defined over R. This is not in R xy because obviously it contains a complex number. So you can avoid this issue by switching this as y squared plus 3. And then you can consider this x minus 2, y plus 3 ideal generated by these two elements. And then it turns out it does define a maximal ideal in your coordinate ring spec of A. So this is a maximal ideal, which you cannot see as a solution set over R because that sort of models this complex point. So this maximal ideal corresponds to a complex point, which you cannot see inside of this R2 picture. There are a lot of more points lurking around. I don't know if that helps.
Yeah, that's good. Thanks. So do you always look at, so if you're working over maybe a different field, do you always just look at
right, that's a general
completion?
So here I didn't really explain this fact. So I just told you that scheme is equivalent to considering the variety for all the field extension of the real extent, the ring extension of your given field. So if k is equal to R, that means your scheme over R is equivalent to considering the variety over C plus the variety over R. If you collect these two information, then that's equivalent to considering the scheme over R. And if you generalize this picture a little bit in terms of growth index, if you have any kind of field and you consider any ring extension, and suppose you can solve your equation over that ring, and you know every variety 0 set, then that's equivalent to considering the scheme.
Okay, cool.
Yeah, this is called the functor of point perspective. If you want to be a little more fancy.
Yoon-Joo, I have another question.
Sure.
Do people generalize schemes to like, I don't know, like a space where it's like locally looks like a scheme? Is that a thing?
Sorry, can you say it again? I didn't get your question.
Do people get to generalize schemes like the ones we talk about today to like some object where it looks locally like a scheme?
Oh, yeah. Thanks for mentioning that. So I told you, thank you, and the talk is over. And at the beginning of the talk, I told you guys I didn't really define the scheme in a most general way. And well, if you know a little bit more, seriously, here's the actual definition. And the actual definition is exactly what you said. So the spectrum of A, given a commutative ring, is a set of prime ideals, not the maximal ideals, because you also need to model the what's called a generic points. And that completes this theory. Equipped with a Zariski topology, this one is, I don't want to mention this, and what's called a structure sheaf, which corresponds to the notion of a function that I mentioned, okay? That's called the affine scheme, and this is like a rigorous, like a full generality definition. And as you mentioned, like the scheme is locally covered by affine schemes. As a manifold, if you consider the definition of a manifold is covered by open balls and you patch them together, that becomes a manifold. So a general definition of a scheme, what we have talked about, I call that just vaguely a scheme, but that was an affine scheme. But a scheme is a space which is locally constructed and passed together the affine schemes, right? So you're right. That's the general definition of a scheme, locally an affine scheme. This is the really correct definition of a scheme in full generality. Yeah, so I did mention the actual definition of the scheme. Thank you. All right, I guess that's all.
Thank you.